9.7 video lecture on antiderivatives. So the idea of what we're going to do with antiderivatives is it's the opposite of a derivative. So we've talked a little bit about this idea already of working backwards from a derivative in a previous section in this chapter. So now we're going to formalize it in this last section in chapter 4. So a function capital F is an antiderivative of lowercase f on an interval I if the derivative of capital F equals f of x for all x in I. So an antiderivative is simply the function that if you take its derivative gives you the original function. So if the antiderivative capital F of f on interval I, then most general antiderivative of f on I is f of x plus c, where x is an arbitrary constant. So one of the things about taking a derivative is that any constant terms go away. The derivative constant is 0. So we can't know when we do the antiderivative what that constant is without a specific example of a function value for the antiderivative. So that's why we're going to add these constants on at the end. So some formulas that will help us do antiderivatives is as follows, and these should make some sense based on the work we did earlier in this chapter. So if, for example, you have the derivative, if you had a function like x to the fourth, right? If that was my antiderivative, that was the original, then the derivative of that would be 4x cubed. So notice if I want to work backwards from f, lowercase f, to get capital F, I need to add 1 to the exponent, and I also have to get rid of this 1/4, which means I need to multiply it by 1 over 3 plus 4. So if I rewrote this as, if I took this derivative and I wrote it as using the antiderivative formula, then it would be 4 times 1 over 3 plus 1 times x to the 3 plus 1. And notice 4 times 1 over 4 cancels. And x to the fourth is x to the 3 plus 1 is x to the fourth. So we get the original function. Okay, so that's how that one works. Then these are just all of the trig functions are just the reverse of their derivative, right? So the derivative, if you take the derivative of cosine, you get sine, so working backwards. So you get all those. Those you just kind of have to use the formula. Then there's the constant multiple rule, which is a constant multiple just gets moved out front. And there's the sum or difference rule that we can break these apart, which should make some sense. So for example, if I were going to do and one more rule just to make things a little easier that I might use is that if your function is a constant, then the antiderivative, well, let's use it. I need to use a different letter here. If my function was just k, then the antiderivative would be kx plus c. So if you have a constant, and you want to find its antiderivative, you just add an x to it. Okay, so let's go ahead and look at a few of these. So for example, if I wanted to find the antiderivative of x to the 7th minus 6x plus 8, I want to look at each one of those pieces individually. So to find the derivative of x to the n, which is what x to the 7th is, I multiply by 1 over 7 plus 1, and then I change it to the x to the 7 plus 1 power. Then for the second piece, I move the constant out in front, and then for the derivative, I do 1 over 1 plus 1 times x to the 1 plus 1. And then for the 8, I just add an x. And then I have to add a c onto the end because I'm not sure what constant might have been there in the original function. So we've simplified this, and this is 1 over 8 times x to the 8th minus 6 times 1/2 times x squared plus 8x plus c, which is 1/8 x minus 3x squared plus 8x plus c. And so that is our antiderivative. And if we wanted to check that, we simply would do the derivative. Okay, so the derivative of x to the 8th comes out in front. You multiply 1/8 times 8. Those cancel. You just get x to the 7th. 3 times 2 is 6x and plus 8. And the constant goes away. Okay, so that's the idea. So let's try a few more of these together. And then I'll have you guys, let's try a couple more of these together, and then we'll have you guys try a couple. So one of the easiest ways to deal with square roots, if you want to do antiderivatives, is to rewrite them as fractional exponents. So this would be x to the 1/2 plus x to the negative 1/2. And so now I can use the formulas from the previous page. So this would be 1 over 1 plus 1/2 times x to the 1/2 plus 1, right? So I'm adding 1 to the exponent, and I'm doing 1 over the exponent plus 1. And so then the second term would be plus 1 over 1 plus negative 1/2 times x to the negative 1/2 plus 1. And then we simplify. So this would be 1 over 3/2 times x to the 3/2 plus 1 over 1/2 times x to the 1/2. And then 1 divided by 3/2 is 2/3. So this is 2/3 x to the 3/2. 1 divided by 1/2 is 2. So this is 2 times x to the 1/2 plus a c added on. Okay. And once again, if you wanted to, you could check that by doing the derivative, and you should get the original function. And then the next one, here's a trig example. So remember, when we're doing a trig example, we want to multiply by 1 over the constant that's on the inside, and then we're going to change it to the appropriate new trig function. So the antiderivative of sine is cosine. So this the opposite of cosine. So this would be negative 1 over the constant, which is pi, times cosine of pi x. Right? Notice the k stays inside as well. Minus 3 times negative 1 over 3 cosine of 3x. Right, so the constant just stays the same. I multiply by 1 over negative, because it's sine changing to cosine, that's the negative cosine, and then 1 over the constant on the inside. And now we simplify. So this would be negative 1 over pi cosine of pi x plus cosine of 3x. And once again, if you wanted to check this derivative, this antiderivative, plus c, you could do the derivative, and you would get exactly what we started with. So go ahead and pause the video for a second here and try finding the antiderivative for the other two functions. Okay, so now that you've given it a try, let's go through these answers together real quick. So once again, when you're dealing with exponents, you do 1 over the exponent plus 1 times the variable to the exponent plus 1 power. So here the exponent is 2, so it's 1 over 2 plus 1 times x to the 2 plus 1 power. Plus, here the exponent is 1, so it's 1 over 1 plus 1 times, 2 times, 1 over 1 plus 1 times x to the 1 plus 1. Constants just stay the same. You're just going to multiply those by whatever you get for the antiderivative piece. Plus 1 times x, and then we add on a constant. And then we can simplify, so this is 1/3 x to the 3rd plus 2 times 1/2 is 1, so those cancel, so x squared plus x plus c. And once again, to check your answer, do the derivative. So the derivative of x cubed is 3x squared. 3 times 1/3 is 1, so we just get x squared. Derivative of x squared is 2x. Derivative of x is 1, and the derivative of a constant is 0, so it goes away. And then here, just like above, the easiest way to do this is to get rid of the fraction and just do negative exponents. And then now I can use the exponent rule that we just had above. So this would be 1 over 3 plus 1 power times x to the 3 plus 1 minus 1 over negative 3 plus 1 times x to the negative 3 plus 1 power plus c. So that's 1/4 x to the 4th plus 1/2 x to the negative 2nd plus c. Okay, and so that's all there is to finding antiderivatives. For now. In the next section, next chapter, we're going to talk in more detail about some of the more complicated functions finding their antiderivatives. So now that we know how to find antiderivatives, we can talk more specifically about initial value problems. So, antiderivatives play in several important roles in mathematics. Methods and techniques for finding them are a major part of calculus, which will be discussed in detail in Calculus 2. Finding an antiderivative for a function f of x is the same problem as finding a function y of x that satisfies the equation dy dx equals f of x. This is called a differential equation. Since it is an equation involving an unknown function y that is being differentiated, to solve it, we need a function y of x that satisfies the equation. This function is found by taking the antiderivative of f of x. We can fix the arbitrary constant arising in the antidifferentiation process by specifying an initial condition, y of x sub 0 equals y sub 0. This condition means the function y of x has a value y sub 0 when x equals x sub 0. The combination of a differential equation and an initial condition is called the initial value problem. Such problems play an important role in all branches of science. The most general antiderivative, f of x plus c, for the function f of x give the general solution, y equals f of x plus c of the differential equation dy dx equals f of x. The general solution gives all solutions of the equation. We solve the differential equation by finding its general solution. We solve the initial value problem by finding its particular solution that satisfies its initial condition. So, if we wanted to find the initial value problem, what we want to do is first find the original function, the general solution, by doing the antiderivative. So start by doing the antiderivative of this function. So if dy dx equals 9x squared minus 4x plus 5, then y equals the antiderivative of this. So we do 9 times 1 over 2 plus 1 times x to the 2 plus 1 minus 4 times 1 over 1 plus 1 times x to the 1 plus 1 plus 5x plus c. So now we can simplify. So 9 times 1/3 is 3. So this would be y equals 3x squared. 4 times 1/2 is 2, so minus 2x squared. Sorry, this one should be x cubed. Plus 5x plus c. So now we have the general solution. So any functions whose derivative is 9x squared minus 4x plus 5 will look like this. Y equals 3x cubed minus 2x squared plus 5x plus c. But now what we want to do is we want to know, in this specific example, what is the function. So if I know that when x is -1, y is -5, I can find c. So I substitute -5 in for y and -1 in for x. And we solve for c. So this is -5 equals -3 minus 2 minus 5 plus c. So -5 equals -10 plus c. So 5 equals c. So my function in this case is y equals 3x cubed minus 2x squared plus 5x plus 5. Okay, so we found the general solution for any function with this derivative, and then with one example, one ordered pair of the original function, we can find the actual specific equation that we're dealing with in this case. So let's go ahead and try a couple more of these together, and then I'll have you guys take a moment and try some of these. So step 1 in any initial value problem is just find the original general solution. So the antiderivative 8t is 8 times 1 over 1 plus 1 times t to the 1 plus 1. And the antiderivative of cosecant squared is, let's look back because I don't remember that one. Cosecant squared is -1 over k cotangent of kx. So this one would be -1 over 1 cotangent of t. plus c. And so then we can simplify. So that would be 8 times 1/2 is 4. So 4t squared minus cotangent of t plus c. And now we can plug in the initial value to find the specific solution here. So -7 equals 4 times pi over 2 squared minus cotangent of pi over 2 plus c. So that's -7 equals pi squared minus the cotangent of pi over 2. Cotangent of 90 is cosine over sine, so that's 0 plus c. And so then we can subtract pi squared from both sides, so it's -7 minus pi squared equals c. So that means we can plug that in for c in our general solution, and we get v equals 4t squared minus cotangent of t minus 7 minus pi squared is our specific solution in this case, or in this initial value problem. Now, we can take this even further and do antiderivatives from more than just one derivative away. So for example, here I have a third derivative. Now, if you're going to work farther back than just one derivative, you need initial values at each step. So notice I have an initial value for the second derivative, I have initial value for the first derivative, and I have initial value for the original function. And that will allow us to take the third derivative and work all the way back to the original function. So if our third derivative was 0, that just means that our original function, our second derivative was a constant, right? Because the derivative of a constant is 0. So the second derivative would be c. And now we can use our initial value. So when the second derivative is -2 when x is 0. Well, we don't have any x's, so c must be -2. So our second derivative equals -2. So now we can do this again, and we can find our first derivative. So if the second derivative is -2, then the first derivative would be -2x plus c. And so now we can plug in our initial value and find c. So the first derivative is -1/2 when x is 0, so -1/2 equals -2 times 0 plus c, so -1/2 equals c. So our first derivative is -2x minus 1/2. And so now we can find the original function. So if the first derivative is -2x minus 1/2, then the original function would be -2 times 1 over 1 plus 1, x to the 1 plus 1, minus 1/2 x plus c. We can simplify -2 times 1/2 is -1. So this is y equals -x to the second minus 1/2 x plus c. And now we can plug in our initial value for the original function to figure out what c is. So y is the square root of 2 when x is 0. So the square root of 2 equals c. So y equals -x squared minus 1/2 x plus the square root of 2. And so there is our original function. So at this point, go ahead and pause the video and try these other two problems. And when you're ready, unpause the video and we'll go through them. Okay, so now that you guys have given these two a try, let's go ahead and work through them real quick together to find the original answers. So in this case, if dy dx equals 10 minus x, then y is 10x minus 1 over 1 plus 1, x to the 1 plus 1, plus c. So that's y equals 10x minus 1/2 x squared plus c. And now we can plug in 0 for x and -1 for y. And so we get -1 equals 10 times x, 10 times, sorry, not x, 10 times, well, 10 times x, but in this case, x is 0. So 10 times 0 minus 1/2 times 0 squared plus c. So -1 equals c. So our answer is y equals 10x minus 1/2 x squared minus 1. And with the second one, we're given the second derivative, so this is going to take a few steps. So if the second derivative is 3t over 8. Then the first derivative is 3/8 times 1 over 1 plus 1 times t to the 1 plus 1 power. So that's ds dt is 3/8 times 1/2 times t squared, so that plus c. So that's ds dt is 3/16 t squared plus c. And now we can plug in our values for that. So ds dt is 3 when t is 4. So this is substitute in. So ds dt is 3 when t is 4. So this would be 3 over 16 times 4 squared plus c. So that's 3 over 16 times 16 is just 3. And so c is 0. So that means our ds dt is just 3/16 t squared. And now if that's the derivative, then s is 3/16 times 1 over 2 plus 1 t to the 2 plus 1 plus c. So this is 1 over 3. The 3's cancel. So this is 1/16 t to the third plus c. And we can plug in this result and see what we get. So we get 4 equals 1 over 16 times 4 to the third plus c. That's 4 equals 4 plus c. So c is 0. So the original function is s equals 1 over 16 s to t to the third. All right. So that's the idea of how to use antiderivatives and initial value prompts. Now, this is a very common application in sciences especially, but in other fields as well. So let's look at some applications of this. Okay, so when Apollo 15 astronaut David Scott dropped a hammer and a feather on the moon to demonstrate that in a vacuum all bodies fall with the same acceleration, he dropped them from about 4 feet above the ground. The television footage of the event shows that the hammer and the feather falling more slowly than on Earth, where in a vacuum they would have taken only half a second to fall the 4 feet. How long does it take the hammer and the feather to fall 4 feet on the moon if they fell at a constant acceleration of negative 5.2 feet per second squared? Okay, so start out by taking the information in this problem and writing out as much as you can. So the first thing I know is A equals negative 5.2. Now, we also know that that is the second derivative of the position vector. Okay? Other things we know is that he dropped it from about 4 feet above the ground. So we know S when at time 0, so S of 0, the position was 4 feet. So S of 0 equals 4 feet. And we also know what the velocity was at time 0 because he's dropping it. So at time 0, it has no velocity. So the velocity would be 0. So not S of 0. The velocity at time 0 would be 0. And we also know that velocity is the first derivative of S. So we can use the ideas we just talked about to work backwards to find an equation for position. And then we can use that to find the time how long it took the feather to hit the ground, which would be, we want to solve this. What is S of t equal to 4, right? Because we want to know when it hits the, not S of t equals 4. S of t equals 0. Because we want to know, when does it hit the ground? So what time is the height 0 if we drop it from a height of 4 feet? So start by taking the first antiderivative of A to get the velocity. So the velocity equals negative 5.2 t plus c. And then we can plug in our initial value for velocity to find c. So 0 equals negative 5.2 times 0 plus c. So in this case, 0 is going to equal c, so velocity just equals negative 5.2 t. And now we can do the antiderivative of velocity to find position. So s equals, the antiderivative is negative 5.2 times 1 over 1 plus 1 times t to the 1 plus 1 plus c. So that's s equals negative 5.2 times 1/2, which is negative 2.6 t squared plus c. And now we can plug in our initial value for s to find c. So that would be 4 equals negative 2.6 times 0 squared plus c. So 4 equals c. So our position function is s equals negative 2.6 t squared plus 4. And so now, if I want to know what time does my position equal 0, at what point does it hit the ground, I plug in 0 for s, and I solve for t. So subtract 4 from both sides, so it's negative 4 equals negative 2.6 t squared. Divide by negative 2.6, so it's 4 over 2.6 equals t squared. And then take the square root of both sides. So it'll be plus or minus the square root of 4 over 2.6. So we can plug that in our calculator. So the square root of 4 divided by 2.6, and we get 1.240 seconds. So t equals plus or minus 1.24 seconds. And because this is an application problem, it can't be negative time. So we're going to say it took 1.24 seconds to fall. Or they took 1.24 seconds to fall. Okay, so how about you all take a minute and try this second problem here. So pause the video, and when you're ready, hit play again, and we'll go through it. Okay, so this one's a little easier than the one we just did. It says a rocket lifts off the surface of Earth with a constant acceleration of 20 meters per second squared. How fast will it be going 1 minute later? Okay, so we can start off by saying we know acceleration is 20, right? Because it tells us that. And we want to know what is the velocity 1 minute later, right? So, except there's one problem here that I did wrong, which is I want to know 1 minute later. So let me add that in because that's going to be important. Okay? And then what we're going to need is we're going to need to get a function for velocity, but we'll need an initial value. So what was the velocity when the rocket lifts off the ground? Well, it's lifting off, so it doesn't have any velocity yet. So v of 0 would be 0. Okay? So we can do the antiderivative of a to get v. So that'll be 20t plus c. And then we can plug in our initial value. So 0 equals 20 times 0 plus c. So that's 0 equals c. So our velocity function is just 20t. And now the thing you have to be careful about is what are the units on velocity here? Well, the units on our acceleration were meters per second squared. So this velocity is in meters per second. Well, right now we want to know velocity at 1 minute. So that means we really want to find the velocity after 60 seconds. So we plug in 60. And we get that the velocity after 1 minute is 1,200 meters per second. Okay. So that's a couple applications of the antiderivative and initial value problems. Now the last thing in this section is defining a new term that has to do with antiderivatives, and this is called the indefinite integral. So the collection of all the antiderivatives of f is called the indefinite integral of f with respect to x, and denoted by this integral symbol f of x dx. The symbol is an integral symbol, and f is the integrand of the integral, and x is the variable of integration. So the interesting thing here is we're saying it's the collection of all the antiderivatives of f. So the indefinite integral is the same thing as the antiderivative of f plus c. Okay? So if I'm asking you to find the antiderivative of something, I'm really just asking you to find, if I'm asking you to find the indefinite integral, I'm really just asking you to find the antiderivative. So to find this indefinite integral, I just find the antiderivative. So the antiderivative of 1 is just 1x. The antiderivative of negative x squared is 1 over 2 plus 1 times x to the 2 plus 1. And then the antiderivative of 3x to the 5th is 3 times 1 over 5 plus 1, x to the 5 plus 1 plus c. So this would be x minus 1/3 x to the 3rd minus 3 times 1 over 6 is 1/2 x to the 6th plus c. And that's all there is. So we already did this earlier in this section. This is just some new notation. So the indefinite integral of 3 cosine of 5 theta is simply the antiderivative. So this would be 3 times, the antiderivative of cosine is 1 over k, so 1 over 5 sine of k theta plus c. So this would just be 3/5 sine of 5 theta plus c. And then the last one doesn't necessarily look like something we know how to do the antiderivative for yet, because right now we'd have to use the quotient rule. But there are other ways we could write this where we would be able to do this antiderivative. This is the same thing as 4 over t to the 3rd plus t to the 1/2 over t to the 3rd dt, which we can simplify a little bit more even and write it as 4 times t to the negative 3rd plus, we can subtract the exponent, so 1/2 minus 3 is t to the negative 5/2 dt. And so now I know how to do that antiderivative. So this would be 4 times 1 over negative 3 plus 1 t to the negative 3 plus 1 plus negative 5, plus, I'm getting ahead of myself, 1 over negative 5/2 plus 1 times t to the negative 5/2 plus 1 plus c. And so we can simplify. So that's 4 times negative 1/2, so that's negative 2, t to the negative 2nd. This is plus 1 over negative 3/2, t to the negative 3/2 plus c. And then this would be negative 2, t to the negative 2nd minus 2/3 t to the negative 3/2 plus c. Okay, and so there is our indefinite integral. Okay, so go ahead and flip over to the next page, pause the video for a moment, and try doing these problems here, and then we'll go over them in a minute. Okay, so now that you all have had a chance to try these, let's go ahead and go through them together. So you're just doing the antiderivative. So the antiderivative here would be 1/2 times 1 over 2 plus 1 times t to the 2 plus 1 plus 4 times 1 over 3 plus 1 to the t to the 3 plus 1 plus c. So that's 1/2 times 1/3, which is 1/6 t to the 3rd, plus 4 times 1/4 is just 1, so t to the 4th plus c. The antiderivative of sine is negative cosine, so this would be negative 5 times 1 over, is negative 1 over k cosine. So k here is 1, so negative 1 over 1 cosine of t plus c. So this would be negative 5 times negative 1 is 5 cosine of t plus c. And then for the last one, you want to use exponents. So this would be the same thing as the indefinite integral of 1/2 times x to the 1/2 plus 2 times x to the negative 1/2 dx. So that antiderivative of that would be 1/2 times 1 over 1/2 plus 1 times x to the 1/2 plus 1 plus 2 times 1 over 1 plus negative 1/2 times x to the negative 1/2 plus 1. So that's 1/2 times 1 over 3/2 x to the 3/2 plus 2 times negative, 1 over 1/2 x to the 1/2. So this is 1/2 times 2/3 x to the 3/2 plus c. Sorry, I forgot those. Plus 2 times 2 x to the 1/2 plus c, which equals 1/3 x to the 3/2 plus 4 x to the 1/2 plus c. Okay. And that is it for chapter 4. So make sure you're keeping up with your video lectures on my math lab and all your homework. If you have any questions about this or any of the other video lectures or anything else, feel free to call or text or email me, and I'll get back to you as soon as possible. Also be watching your email for updates on video lectures, and know that we have now finished chapter 4, so you should expect to have a chapter 5 test on my math lab coming up in the next couple of weeks.